Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Oozy or explodey? Today we're going to start a unit, Houston, we don't have no problem, about volcanoes. Do they ooze or do they explode? Let's look at an oozy volcano. That was cool. Hot, boiling lava. What about an explodey volcano? Whoa, that was a lot of energy. Volcanoes. Volcanoes have fascinated the world and probably fascinate you because they're so awesome. It turns out there's actually 4 kinds of volcanoes. You can see them pictured here. And they mostly ooze or explode. There's really 2 big categories. The oozy ones is the big one here, which we call a shield volcano. Hawaii is a shield volcano, the big island of Hawaii. And then there's the explodey kind, and that's the composite one that you see right here that is, well, it explodes. We're going to talk about why that is a little bit later, but I want you to notice something about the shield volcanoes. Notice how they tend to be long and skinny, they're not very steep slopes, and the explodey ones, or the composite volcanoes, they tend to be much steeper. And then there's 2 other kinds. There's the cinder cone and the lava cone. So 4 kinds of volcanoes, but really the 2 big ones are oozy and explodey. Again, oozy. What's oozy mean? That's a shield volcano, not very steep slopes, and they can be huge in their width, if you will, and ones that explode have steep slopes. Now let's go a little bit deeper and talk about why do some ooze and why do some explode. It all comes down to a key term. It's called this. Viscosity. Viscosity is the resistance to flow. So liquids have viscosity. Maybe you've changed the oil in your car and they have these 10W40 and 5W30 and all these numbers, and that is a measure of the viscosity. It's like the thickness of a liquid. A more viscous liquid might be syrup compared to water. And there are some volcanoes that tend to ooze out. They have high viscosity, and the ones that explode, frankly, they have low viscosity, so they don't have a chance to sort of just escape and just flow. Instead, boom, they explode. Another key term that's going to make a difference here, I think it's one of the coolest things and scariest things about volcanoes of all, is this. Something called a pyroclastic flow. A pyroclastic flow is this. So when an earthquake erupts, oftentimes it's associated with a pyroclastic flow. It is one of the most amazing things in nature. Take a look.
This is a pyroclastic flow. It's racing down the side of a volcano, hot, fast, and deadly. This, however, is a replica, created in a lab in New Zealand. But it's providing new insights into this dangerous phenomenon. Pyroclastic flows are fast-flowing currents of rock, ash, and hot gas produced during volcanic eruptions. They can move at several hundred kilometres an hour and can be hot enough to kill in an instant. But no one knows exactly how these pyroclastic flows move. Thousands of kilograms of dry volcanic material should produce a lot of friction, but they seem to flow like a liquid. So what's really going on inside? It's extremely difficult to study a pyroclastic flow on an active volcano, so these researchers made their own. They mined real volcanic material, mixed it with heated gas, sent it hurtling down a chute, and filmed what happened. Through heat-proof glass, they were able to see the ash cloud on top and the denser particles underneath. But surprisingly, at the very bottom, they found that a thin layer of gas had formed. This layer was acting like a lubricant, decreasing the friction and allowing the material above to move further and faster. This new understanding of the anatomy of pyroclastic flows could help volcanologists make better predictions for future eruptions. And maybe this volcano in a lab will help save lives.
What you've just seen is hot gas and rock and ash racing down the hill upwards of 60 miles per hour. Anybody who gets caught in its wake, yeah, I think you get the picture. But this has to do with this, which relates to Ooze, which relates to exploding. So in your notes, go ahead and fill out this table. So we've got the composition. The composition has to do with the type of rock. Remember back in our mineral unit, we learned about this. This first one is basaltic. That fancily means has basalt in it. And basaltic happens to be mafic. Remember, mafic is the darker rocks, right? The second one is andestic, and that is what we'll just say intermediate. And if you recall, these are dark rocks, medium colored rocks or minerals, and the last one are the felsic rocks. These tend to be more rich in silica. All right, so mafic, basaltic to felsic, it's like a continuum. Now, what about the gas content? What's interesting about a volcano when it erupts is often there's gases trapped, and when the gases expand, you get really, well, that's when the explosions happen. So the gas content of this tends to be low, 1% to 2%. For the andestic ones, it's 3 to 4%, and then this is 4 to 6%. Now gas, as you recall, maybe back in a chemistry class, has the ability to expand to great, great places. All right. So the viscosity, or the temperature, the eruptive temperatures, this is hot, 1,000 degrees to 1,250 degrees. That's the hottest of them all. This is 800. I want you to kind of figure out as I'm writing these down. Can you figure out which ones are the Ooze and which ones are the explodies, right? And this is 650 to 900. So still hot, right? But not as hot. So we've got varied temperatures. So what about the viscosity? The viscosity has to do with how thick the liquid is, right? And so in basaltic, this is going to have a low viscosity, means it flows well, more like a watery substance. This will be a medium, and this will be a high. Meaning it's got high viscosity, means it's really super thick, syrupy, actually even way thicker than syrupy. And then the tendency for you to have this crazy pyroclastic flow, which is super crazy, awesome, and scary at the same time, this one would be just low, medium, high. And that leads us to, do we have Ooze volcanoes or do we have exploding volcanoes? All right, so we call this right here, the low ones, we call them the shield volcano. We learned that a bit earlier. But also as a note, these are also the cinder cones. So these have both. It's basically a cinder cone is kind of like a smaller shield volcano. And these are composite cones. We haven't really talked about that as a type. It's kind of a marriage between composite and the cones. And this is lava domes and composite volcanoes. So we have basically, right, if you get the picture, this is exploding and this is Ooze. And it's like a continuum, and you get more and more as you go further. So this has to do with the types of volcanoes, but there's another way to look at volcanoes. There's like basically alive volcanoes and dead volcanoes, or dormant volcanoes. We actually use a fancy term, which I can't spell very well, for a dormant volcano, or one that's kind of a quiet one, right? It's Q-U-I-E-S-C-E, and quiescent, I think is how you would pronounce that. And these are, if you will, the inactive volcanoes. So you can classify as inactive volcanoes. You can classify them as active or inactive. And then lastly, let's think about this. When we talk about volcanoes and what kind of types they are, I don't know if you get the idea, but there's really two factors that are playing a role: temperature and composition. Composition is the rocks that are made of it, composition and temperature right here. And that's temperature of the eruption. But, I mean, the viscosity really is the key player in determining what you're going to have. But what causes viscosity It's temperature and what the rock's made of. Because some rocks have higher melting points. If they have a higher melting point, then they're going to tend to be, well, they're felsic, and they're going to have less of a chance to explode, or more of a chance to explode, pardon me. And if you have a high temperature, I mean, you could, conceivably, if you had a super crazy high temperature with felsic rocks, you could indeed get it to be ooze and flow, but it's not the case. It just must be the temperature of the Earth. I'm frankly not 100% certain. But volcanoes, what causes volcanoes to erupt? Well, we're talking about more in the coming videos, but it all comes down to, you know, you've got a magma chamber underneath the Earth, and it's at different conditions depending on what it's made of, composition, and what the temperature is, and then also what the gas content is, and then things start happening. And it's a sight to see. I've never seen one in person, but the videos are astounding. Houston, we don't have a problem. We'll see you in class.